Okay, to summarize, a neuron at its resting potential, right, has a charge difference, a charge gradient that's maintained, largely because the membrane of the neuron is a phospholipid bilayer that's impervious, impermeable to the passage of charged particles. So sodium can't really get inside, right? And potassium can't really get outside. There are some leakage channels, right, for both sodium and potassium in a neuron at rest. These are non-gated channels. They're holes that are always open. But there aren't that many of them, particularly for sodium. And the neuron, because it's got this difference in terms of the distribution of charges, more positive charges on the outside versus the inside. So more negative, on the inside of the cell versus the outside. And if you put a potential or an electrode on the inside and you put one on the outside, well, you'll detect that difference in charge about minus 65 millivolts, thousandths of a volt, more negative on the inside versus the outside. And that difference in charge is going to rest. It's going to stay the same. It's going to stay constant. And in order to, get a neuron to have action between the potentials, you really need to open a lot more channels, a lot more holes to allow ions, sodium and potassium, to distribute back and forth across the membrane, driven by the forces that we've been discussing in this class, right? Including the electrical force, opposite charges attract, the concentration gradient force, things move from areas of high concentration to areas of low concentration. But in a neuron at its resting potential, there's a certain level of charge polarization, and it's minus 65 more negative inside than outside. And that difference will rest, will stay the same. So that level of polarization is sort of constant. However, the neuron will actually alter that relationship in terms of charge under certain circumstances. It can actually make a bigger difference in charge. It can actually get more negative than minus 65 versus the outside. It can move to something like minus 80, inside in terms of millivolts versus the outside. But in order to do that, it actually has to move ions across the membrane. So, for example, if you open more channels to potassium, potassium's an ion that's in high concentration on the inside of the neuron, right? And because of that very high concentration, the concentration gradient force really wants to drive it from the inside where it's at high concentration, right? Because of the pump, it wants to drive it out, right? Of course, the electrical force, right, when it's minus 65 on the inside, well, potassium is a positively charged ion. So the electrical force states that opposites attract, right? So the potassium is going to want to stay inside because of the electrical force. So these forces are opposed to each other, right? And there's a complicated equation. In other classes, we go into it. But basically that can determine, given a particular charge difference, a particular level of polarization between the inside and the out, and the specific concentrations of ions across the membrane, it'll tell you which direction in the ion will move, which force will win, right? But I'm just going to tell you in this class that at minus 65, at the resting potential difference, that difference that's maintained across the neuron's membrane, by the pump and the impermeability of the membrane at rest, well, potassium is going to go out. So the concentration gradient force, which wants to drive it out, is stronger than the electrical force, which wants to keep it in. So at the resting potential difference, if you open more channels to potassium, well, the concentration gradient force is initially going to win, right? It's going to drive more of that potassium out. It's going to want to move out. And as it moves out, it is a charged particle. It's positive ions that are going from the inside, where it's minus 65, to the outside. And so you're removing positively charged ions from the inside. You're going to be increasing the polarization. You're going to be making it more negative on the inside because you're removing positively charged ions. And as you do that, you, what we say, hyperpolarize the membrane. You actually make the membrane more negative inside than it was at rest. It's not at the resting potential level of polarization of minus 65. It goes up to minus 75, minus 80. But as you do that, right, as you move more of this, potassium, positively charged potassium out, well, you're increasing the polarization, hyperpolarizing, and you're increasing the electrical force, the pull, of the opposites. So at a certain point, if you added more, permeability to potassium, you open more channels that let potassium, flow from the inside out, driven by the concentration gradient force. Well, eventually you're going to get to a new equilibrium, right? Where you're going to have more of the potassium outside, but it'll stop, on balance leaving. And you'll have a new kind of hyperpolarized membrane potential of around, let's say, minus 80, because the forces will now be aligned. Now, you could also do what we call depolarize a membrane, right? A neuron can reduce the difference in charge inside versus the out. And it also, to change the polarization, it's got to allow for the movement of ions, so ions can move across that membrane. And to depolarize, a very good ion that's all set up, to really want to, to move is sodium. Sodium is found in high concentration, and review this, right? It's found in high concentration at rest outside the membrane, because the membrane's not very permeable to potassium, right? There are only a few of those leakage channels. The pump is very busy kicking out any sodium that gets into the extracellular space. Well, you have sodium then in a high concentration outside the membrane in a neuron at rest. It is positively charged, and the inside of the neuron is at minus 65. So both the concentration gradient force and the electrical force want to drive sodium from the outside of the membrane to the inside. There's no confusion there about which direction it's going to be going in a neuron at rest. So if we opened more channels, right, to allow for for sodium to go through, well, sodium's going to go in. We know that because the concentration gradient force will drive it in, and so will the electrical force will drive it in. As you bring more positively charged ions, right, from the outside, to the inside, where it was at minus 65, think about what happens to the charge difference across that membrane. You are going to be reducing it. You're going to be going from minus 65, right? You're bringing in positive sodium, to minus 60, to minus 55. You are reducing the polarization, and we call this depolarizing the neuron. And the reason we're talking about polarization, hyperpolarization, and depolarization is because in order for a neuron to generate what we call an action potential, this could be the rapid redistribution of ions across the membrane, you're going to have to open a whole bunch of channels to let sodium and potassium go back and forth. And these channels at the resting potential are clearly closed. They are gated. But depolarization, the reduction in that charge difference, the reduction in the voltage, the level of charge difference across that membrane from minus 65, we're going to see down to a threshold voltage. It'll be around minus 55, will cause a lot of these channels to open, to ungate, and allow for rapid redistribution of charges across the membrane and a lot of action between those potentials, the one inside versus the outside. So I want you to think about this. Depolarization leads to the initiation of an action potential. It excites a neuron electrically. It gets it to start sending an electrical message. We'll talk more about how this happens in subsequent video lectures. But hyperpolarization actually results in inhibition. It makes it less likely to fire because you're taking the charge difference away from that critical depolarized threshold that will allow for channels to open.